idea now is to work on principal component analysis, which is called PCA, using the covariant matrix, eigenvalues, and eigenvectors to find axes in which most of the covariance is, so I can project the data on this axis, so I can make the data in less using less dimension and more capturing what differentiate between the values. For example, so you can understand what we are going to do, this is a very simple example. I have three individuals, each one has height and weight, and I want to see how can I project them. Instead of using two dimensions to describe each of the individual, I want to get one dimension which describe each of the individuals. Now, as you can see, the individual ones is height is 65 and weight is 130. The second one is this and this, the third is this and this. As you can see, the first is the most small and the third one is the biggest one. So if I want to describe it in one dimension instead of two dimensions, I can say that the first one is, let's call it -2 value, and the second one is between them, so it's 0, and the third is the biggest one, so it's 2. So the new coordinate, like catching the, the relationship between the data, which correspond to the difference. So this is the original data, and now when we will transform it using a principal component analysis, using the first principal component, we will get to this new data. As you can see, the new transformation, the new data transformed to an axis using 1 and 1 as the new axis. So the first one gets a -2, the second one 0, and the third gets a 2. After normalization, it's quite saying that the both values are important in the same way, in the same direction, but after normalization I get this values. Uh, so you can see how it captured the relationship between the values. This is the first principal component. This is the first eigenvector which correspond to the highest value eigenvalue. So let's see how it goes, so maybe we'll understand what happened. So again, we start with this table. This is the data we have, and we want to reduce the dimension to a dimension that capture most of the variance between the data. So we start with these three lines, three individuals, two dimensions, height and weight for each individual. So what we start with is normalizing the data. In order to normalize the data, what we do is we will take each value and reduce the mean from it and divide the value by the standard deviation, normalizing the data, and you will see it happen. Here it is. This is how we standardize the data, normalize it. We take the value, we take the mean of the weight of all the individuals, which is 70, and we divide by the standard deviation of the height. We're doing the same for weight. The mean for weight here is 140, and the standard deviation is 10, so we normalize each of the values. We get these new values for the normalization. You can see how it goes. You can calculate the weight, the mean for height, the standard deviation for height. Each value take it, I take down the mean height from it, sum it up after taking the squared and divide by n, and I get the standard deviation. The same I do for weight, calculating the mean, calculating the standard deviation. Now I calculate the covariant matrix. Now the covariant matrix tell me what is the relationship between the uh, values. Like when I take the covariant matrix between, let's say, height and weight, those are the two dimensions I use, therefore those will be what I will use for building the covariant matrix. So I will have covariant of height and height, covariant of height and weight, covariant of weight and height, and covariant of weight and weight. So for the covariance of the two variables height and height, I take, this is the formula for the covariance of two variables. I take the first one, the first instance, minus the mean of x, and the second value minus the mean of its values. And I know the mean and the mean we just calculated, and the values, the raw values of each height and weight we know, so we can, and we know how many instances we have for each one, which is 3, so we can calculate the covariance as you can see here. The covariance of the same thing uh, with the same thing is just the variance. So the covariance of height with height is the standard deviation squared, which is the variance. So which is the, okay, let's call it standard deviation squared because it's always positive. So it's 25 because standard deviation of height is 5, so taking the squared is 25. Now the weight is 100. Now the covariance between height and weight is taking this formula and doing so. So 65 minus the mean of the x, 130 minus the mean of the y, and etc divided by 3, uh, and I'm getting the covariance between height and weight, and the covariance between weight and height will be the same. So height and height is here, weight and weight is here, height and weight is here, and weight and height is here. So this is the covariant matrix. Now I want the eigenvector of this matrix which correspond to the biggest eigenvalue. This will give me the direction with the most variance. So this direction with the most variance, I will project my data onto it to capture in reduced dimensions most of the variance between the values, between the individuals, which will help me reduce dimension and capture most of the meanings of between individuals. As we saw, we translated the height and weight to one value which represents the size of the individual. We saw -2, 0, and 2. As you saw, this is the initial values for the original data, height and weight, and we will transform it to one value which will represent the size of the individual. The first one is the smallest, the second is in between, and the third is the biggest one. You can see that this is what happens. The first one is the smallest, the second is the middle, and the third is the biggest. And we will find the eigenvector that correspond to the biggest eigenvalue of the covariant matrix, which will represent the axis, the, the direction which I need to transform the data onto. I will project the data using, let's say, inner product if you want, or if you want scalar multiplication, or whatever you want to call it, to project the data, the normalized data, onto this eigenvector which corresponds to the biggest eigenvalue of the covariant matrix, to capture most of the variance between individuals and to reduce the dimensions. So how will I get this? So I got the covariance as we saw, the covariant matrix. Now I want to get the eigenvalues, and then I'll get the eigenvectors, and then I will choose the eigenvectors, the eigenvector which is which correspond to the biggest eigenvalue. So how do you calculate eigenvalues of a matrix? If I have a matrix, I want to calculate the eigenvalues. So I take the determinant of my matrix minus the eigenvalue times the unit matrix, and I want to get it to 0. What the solution to this are the characteristic equation, and the solution to the characteristic equation are the eigenvalues of the matrix. So I did it. I took the covariant matrix. I want to find its eigenvalues. So I take the covariant matrix, I call it A. I subtract from it the lambda, which will be the eigenvalues. I will find the eigenvalues. Here are my two eigenvalues. So I subscribe the scalar lambda. It's a scalar, it's just numbers, times the unit matrix. So I can subscribe matrix for a matrix. And I want the determinant of this to be 0. So here is the covariant matrix. Here is after subtracting lambda times the unit matrix. This is what I get. And I take the determinant of this and equals 0. This is the equation I want to solve, and this is how it goes. Maybe there will be mistakes in the calculations. I'm sorry, but put attention. Maybe there are mistakes in the calculation here, but it doesn't really matter. I just want to show you the idea. But remember, the results may be wrong with the values. Okay, so we want to get the eigenvalues, so we calculate the characteristic equation. Here it is, and we want to solve it. So we use the quadratic formula to solve this equation and get the values. Maybe there is a mistake here, but never mind. But put attention that there might be a mistake in the values. So the first eigenvalue is this, and the second eigenvalue is this. Note that the first eigenvalue we got is the bigger one. So we want to find the corresponding eigenvector which will capture the most of the variance because its eigenvalue is the biggest. So let's calculate the eigenvector which corresponds to the eigenvalue lambda 1, which is this value. So how do you calculate eigenvalues? You take this and solve it. Our matrix minus the eigenvalue times the unit matrix, all of this times the eigenvector we want to find. Let's call it v1 equals 0. Solve it and get v1 values. This is the eigenvector. So a minus the eigenvalue times the unit matrix will get us this times the eigenvector v1 equals 0. We want to solve it, and we are solving this linear equation, system of linear equations, and we get the result. Again, maybe there are mistakes in the calculation, but doesn't matter. So this is the result. This is the eigenvector which correspond to the first eigenvalue, which is also the bigger one. So the second eigenvalue is the smaller one, is this. We can also calculate its corresponding eigenvector, but this eigenvector capture less of the variance because it corresponds to the smaller eigenvalue. Okay. Now let's call this the principal component 1 because it corresponds to the bigger eigenvalue, and this will be principal component 2, which corresponds to a smaller eigenvalue which corresponds to the second eigenvalue. Okay, now we got the principal components, which are the eigenvectors. Now we want to use the bigger one. We want only one dimension, so we will project the data on this axis 1 and 1. Let's do the transformation. Again, we have the standardized data, the normalized data. We subscribe the mean and divide by the standard deviation to get for each value, height and weight to get the normalized data. And now we project the data onto the new axis, onto the first principal component. So we take -1 and -1 and project it onto the eigenvector by doing a scalar multiplication. We're taking 0 and 0 and multiplying by 1 and 1, the first eigenvalue, the first principal component, PC1, and we take the third and multiplying by, again, the principal component, the first principal component, we project it onto the first principal component. So we transform the data, each one, this, we normalize it and project it onto the principal component 1, which is the first eigenvalue. We took this, standardize this, project this onto the first principal component. Wait. Yeah, okay. Yes, this is what you did. We took this and again normalize this, and project this sample onto the first principal component, onto the first eigenvector which corresponds to the bigger eigenvalue, and we got this new data. Normalize project, normalize project. Okay, so this is those are the results for the first sample. This is the new value for the second, for the third, and again it captured the variance and told us in one component, one dimension instead of two, what is the relation. The first is the smaller, the second is between, and the third is the bigger one. You can understand it also from here with two dimension, and you can understand it much better with one dimension right over here using the first principal component, which is the eigenvector. So I can call the first eigenvector the first principal component. As you can see here, the first eigenvector is the first principal component. Okay, so this is it. This is how we use the covariant matrix and all the standardization of the data to reduce dimension and using the principal component analysis. You can also do it using other things like taking the singular value decomposition of the covariant matrix again, but it's the same idea. Using the singular value decomposition, you get the again the uh, singular values which correspond to the eigenvalues and the corresponding principal components in the U or U I think matrix. Again, they correspond to the eigenvectors, but the core idea you saw here is the core idea of the principal component. Using the SVD or other method is just another method to do the same thing. Take the data, calculate, as you can see, you saw here. Take the data, calculate the covariant matrix. We can also standardize it. We didn't standardize. Can we normalize the data before calculating the cov matrix? As you can see, normalizing the data before calculating the covariant matrix might also be a good idea, but in this example we didn't do it, but we could do it, and it may be even better to do it because you will use much smaller values and the covariance calculation will be much easier. You can see this much better looking covariant matrix. Maybe there are mistakes, but when maybe we should have done that instead of all that mess that we did. But the idea is the same. We could standardize and normalize the data before doing the covariance. Maybe it's better. We should have done that. Maybe it's better practice. But again, the idea is again calculate the covariant matrix, standardize the data, calculate the covariant matrix. Here's the covariant matrix. Calculate the eigenvalues. Here are the eigenvalues. Here are the eigenvalues. For each eigenvalue, calculate the corresponding eigenvectors, which are the principal components. Principal component 1 is the eigenvector of corresponding to the bigger, not the first, the bigger eigenvalue. Principal component 2 is the eigenvector corresponding to the second biggest eigenvalue. The size of the eigenvalue is important. And then project your data to the eigenvectors you want. Here we projected the data only onto one eigenvector, only onto one principal component, not two. But we could use one principal component and then project to the second principal component, so we have two principal component, or 3, and etc., if we had more eigenvectors or more principal components, which we don't here. We have only 2. But we only projected into one principal component in one eigenvector, so we reduced the data from 2 dimensions into 1 dimension. Okay, so covariant matrix is very important here, and finding the eigenvectors and eigenvalues of these is important, and standardized data and normalizing is better than what we did here. Don't forget it. Thank you very much. If there are any mistakes or correction like I did with the normalization that I should have done, please tell me. Thank you very much. This was about principal component analysis using covariant matrix, eigenvalues, and eigenvectors and standardizations. And that's it. Thanks, Deepstick. If there are any mistakes, there may be mistakes in the calculation. I'm sorry, but I'm hoping that the idea passed. Thank you very much, and that's it.